Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning.
Waalaikumsalam, teacher.
Okay, so today we continue our discussion on science subject. So yesterday we have discussed about, we start with electricity and magnetism. What is that?
The fish. Yeah, what do we do with this fish?
Fatin, Natasha.
Before I get grammar police.
Please switch off your microphone. Okay, so yesterday we have discussed about the most important thing is about the how generator that produce electricity works. So we go back to this one, generator. So the concept of generator itself is based on the movement of two important component of generator itself, that is wire and also the magnet. So if we move whether wire or magnet between them, so the movement will cause the production or the generation of electricity. So if you can see from this generator model, so this generator model, you can see from here that the magnet, this magnet, so between the magnet we have coil of wire, and then this coil of wire is connected to the crank, in which this crank will be moved to make sure that the coil of wire can be continuously moving. So because the movement of coil of wire or the movement of magnet will cut the magnetic field, so it will produce electricity. So based on this, what we have discussed yesterday, so in order for us to move the wire or the magnet, so we have some instrument that can move the wire itself. For example, this generator model, usually all the generator, they will move the coil of wire. So in order for generator to move its coil of wire, so we are using something like this, crank. So manually, when we push this one, so it will move the coil of wire between the magnet. So the movement of this one will generate electricity. So very important, the main concept on how a generator works is based on the movement of coil of wire. That is very important. So same thing as this one. You can see this one is a wire, okay, between the different poles of magnet. So when this coil of wire is moving or make around between the magnet, so it will produce or generate electricity. So this diagram shows how we put something like this one. When we rotate the axle, so we can move the coil wire between the magnet. So by doing this, we can cut the magnetic field and the electric current will be produced. Yeah. So now we will look into the general concept that being used in the power station on how electricity is generated. Yeah. So we will look into every power station with different energy sources. Yeah. So what is the most important thing that how the generation of electricity can be produced through the movement of the coil of wire. Eh? Okay, so now in general situation, for example, in power station, okay, in order to generate electricity, so we can see in power station, there is a generator inside. So this generator will produce electricity. You can see from here, this generator will produce electricity as we have discussed previously. So how we want to make sure that the generator can function well? So what happened in power station is we are using what we call as a turbine. Yeah. So this turbine will move the generator to generate electricity. So in order to move this turbine, so we require a source of energy to make sure that the turbine is moved. Yeah. So because this turbine is very large in size, so we require a very large amount of energy sources. Yeah. So all the power station will have what we call this turbine. Yeah. So this turbine will move, and when this turbine move, so it will move the coil wire inside the generator, and the generator will generate electricity. So in order for the turbine to move, so we require a very large energy sources. So these energy sources will supply energy to move the turbine. So when turbine is moved, so the generator will function to generate electricity. So this is the different parts of how we can separate the function of sources of energy. So these sources of energy, the main function is to move the turbine. So most of the power station will have this turbine in order to move the generator. Yeah. So the different kind of energy sources that we have, the main function is just to move the turbine. So we can see, for example, the first one, power station that using non-renewable energy sources such as diesel, natural gas, and coal. Yeah. Okay, so now the position of energy sources, okay, for example, this one, the fuel used here, whether diesel, natural gas, or coal. So we use fuel here, and then this fuel will be in a high temperature, produce heat energy. So what will happen is it will heat the water inside the boiler. So when water is heated, it will produce steam in high temperature. So this steam will enter into the turbine, and because of the high temperature and high movement of steam, so it will move the turbine. Yeah. So when the turbine move, so it will make the coil wire inside the generator move, and then electricity is generated. So this is the simple explanation on how power station using energy sources to generate electricity. So the difference is only based on the energy sources used to move the turbine. That is the function of the energy sources. Yeah. So I hope that you can understand the simple flow of how the power station, yeah, using the energy sources to generate electricity. So given here, the flow on how electricity is produced, yeah, mechanism, burning of fuel, and then it will boil the water, and then the steam produced will move the turbine, will rotate the turbine, and then the generator will produce electricity. So this is the mechanism, the general mechanism on how power station produce electricity. So based on the energy change, chemical energy from the burning of fuel, so produce heat energy. So this heat energy will change into kinetic energy, in which the turbine is rotated, and then the generator will produce electrical energy. So this is the mechanism and energy changes that occur in the mechanism of this power station. Yeah. So this is the power station that are using energy sources, non-renewable energy sources. So we will look into the power station that using other type of energy sources. For example, the example given for the number 2, power station that using solar energy. Yeah. So this solar energy, okay, this one. So they are using the energy coming from the sun. So they change it into the electricity. Okay. Hydroelectric power station. So hydroelectric. So this power station using water. So they build a dam, yeah, and then this dam will have something like this, in which this dam will allow the flow of very high speed water. So this very high speed water will rotate the turbine inside the power station. So this turbine will rotate, and then it will rotate also the generator to produce electricity. So the concept is same. Yeah? Turbine is used to rotate the coil wire inside the generator, so it will produce electricity. So on how we want to rotate the turbine, we are using the flow of water. So when the high speed flow of water, okay, touch the turbine, so the turbine will rotate. Yeah? So that's why we are using hydroelectric. That's why we built a dam, just because to collect the water, and then to make sure that the water flow with a high speed to rotate the turbine. So that is the concept used in the hydroelectric power. Yeah. So the mechanism given here, high dam store water. So this water flow from high level to low level, and then flow of water rotates turbine, and generator produces electricity. So energy changes here, gravitational potential energy to kinetic energy, and then produce electrical energy. Yeah. Next, power station that use wind energy. Yeah. So same thing, the mechanism moving air. So move blade. So blade rotate turbine. Okay. And produce electricity. So energy change here, kinetic energy to electrical energy. So this is most several countries in Europe using this type of power station in which they are using the potential of wind, moving air in order for them to rotate the turbine. So this is the example of power station using wind energy. Power station next is nuclear. Okay, using nuclear energy. Yeah. Okay, so this nuclear power plant so will produce energy in which this energy will heat up the water and then produce steam, and same concept, it will rotate the turbine and generate electricity. So the mechanism, nuclear reaction, boil the water, produce steam, steam rotate the turbine and electric current is produced. Yeah. Power station using biomass. Okay. So biomass, this one. So when biomass is burned, so it will produce some kind of hydrocarbon substances. So these hydrocarbon substances, when burned, it will produce a lot of heat energy. So this heat energy will heat the water in the boiler, so produce steam. So the steam will move into the turbine. Turbine will rotate and generate electricity through the generator. Yeah. So this is the simple explanation on how power plant function. Yeah. So the mechanism here, biomass produce methane, boil water, and then steam produced will rotate the turbine and generator produces electricity. So energy change here, chemical energy into heat energy, kinetic energy, and then electrical energy. So that is the explanation on different type of power station. You can see from all the power station, so the same concept is used in which the different type of energy sources is used just to create a rotation of turbine. So the turbine is used in most of the power station, but the difference is only based on the energy sources to rotate the turbine. That's all. So I hope that you can remember the different type of power plant based on the different type of energy sources. The same concept is just they are using the turbine to rotate the generator. Okay, so uh, we look into the outside. Outside means Alisha Aiman.
There's no such student in 3 amethyst.
Yes. Why, Alisha, why not using the MOE? Never mind. Okay, so we look into a revision about this one. Okay.
EMF or alternating current. Working principle of an AC generator. An AC generator
So we look
works
into
on the
revision
principle of electromagnetic induction.
the
In
principle or
electromagnetic
concept
induction,
used in the
when there is a relative motion
generator
between a
first.
coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily zero. Hence, the induced EMF at this position is zero. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux.
Okay, so that is the revision on how induced current is produced. So now we look into the about the power plant on how power plant generate electricity. Yeah. So wait a minute. Which one? Okay.
All generators use induction to create an output voltage. When the output of a generator is connected to a circuit, the induced voltage causes current to flow through the circuit. There are 3 requirements for inducing voltage. First, a conductor must be available to carry current. The second requirement is a magnetic field. Third, there must be relative motion between the conductor and the magnetic field. In this illustration, a wire is wrapped around a metal ring. The wire serves as the conductor that carries the current that results from induction. The second requirement, a magnetic field, is created using a magnet. A permanent magnet like this one can be used to induce voltage, but the magnetic field it creates is very small. Electromagnets are used to create controllable magnetic fields that are strong enough to induce large amounts of voltage. This is a basic electromagnet. It consists of a coil of wire wrapped around a metal bar or core. When electric current from a source of direct current flows through the wire, a large concentrated magnetic field is created. The wire may be referred to as the field winding because it helps to create the magnetic field. The third requirement for inducing voltage is relative motion between the magnetic field and the conductor. Here's an illustration that shows how voltage is induced when the electromagnet rotates. This electromagnet has a north pole and a south pole. The magnetic fields at the 2 poles are opposite in polarity. As the electromagnet rotates, the magnetic fields cross the conductor and induce a voltage. We can say that the north pole induces a positive voltage and the south pole induces a negative voltage. Generator output can be represented as a sine wave that is plotted on a graph. On this graph, the vertical axis represents the strength of the voltage, which can be positive or negative. The horizontal axis represents time. As the electromagnet rotates, the relative positions of the electromagnet and the conductor affect generator output as shown on the graph. When the electromagnet is vertical and the magnetic fields don't cross the conductor, the voltage is 0. Now, as the electromagnet rotates through the first quarter of a complete revolution, the output increases to maximum in the positive direction, and then drops to 0 again as the magnet reaches a point 180 degrees from its starting position. As rotation continues, the output reaches maximum in the negative direction as the south pole of the magnetic field crosses the conductor. The output decreases again as the magnetic field moves away from the conductor. Let's expand the simplified illustration of a generator to show some other components. The metal bar and the wire that is wound around it can be called the rotor core. In the illustration, the rotor core is connected directly to a DC power source that appears to rotate with the core. However, the DC power source for a generator is usually stationary. One way to cause current flow from a stationary DC source to the windings that encircle the rotating metal bar is to use slip rings and brushes. The slip rings are usually made of copper and they turn with the generator shaft. One slip ring is connected to the negative lead of the rotor winding, while the other slip ring is connected to the positive lead. Inside a generator, the slip rings, the rotor core, and the wires connecting the slip rings to the windings all rotate together. The brushes are typically made of a carbon material that brushes against the slip rings as they rotate. Current flows from the negative side of the DC power source through one brush to a slip ring. From there, the current flows to the winding around the rotor core where it creates a magnetic field. To complete the path, the current flows from the winding to the other slip ring, then to the brush, and back to the positive side of the DC power source. The component of the generator that doesn't rotate can be referred to as the stator. The conductor that is wound around it can be called the stator winding. The ends of the conductor are connected to the power system. The output from the generator we've been looking at is single-phase voltage. Single phase means that there is only one voltage output. This is because our example has only one stator winding or conductor. However, most generators used in power plants are designed to produce three-phase voltage. Let's see how a three-phase voltage output can be produced by modifying the simplified generator illustration. If we add two more stator windings, voltage will be induced in each winding as the magnetic field crosses the wires. The result is a three-phase output. As the rotor rotates, maximum voltage is induced in each of the three stator windings at different times. This sine wave represents one of the three phases. Maximum positive voltage occurs as the field around the north pole of the electromagnet crosses the first stator winding. Maximum voltage in the second phase occurs as the field crosses the second winding. At this point, the first phase voltage is decreasing. In the third phase,
Okay, so same thing, the concept of how generator works. So we will look into the next. Okay.
the function of a turbine is to convert energy contained in steam to mechanical energy that is used to turn a generator. A turbine is an enormous machine and may seem indestructible, but in fact, a turbine is easily the most delicate and precise piece of equipment in a power plant. To operate a turbine safely and efficiently, it's important to have a basic understanding of turbine construction and operation. In this part, we'll take a look at the various components of a turbine. As we do, we'll be using common names for turbine components. Keep in mind, however, that your plant may use different designations depending on the manufacturer of your turbines. This is a diagram of a simplified steam turbine. Turbines are composed of moving parts, stationary parts, and systems of pipes and valves. We'll start with the moving parts, the shaft and the wheels. The turbine shaft runs the entire length of the turbine. This end is connected to the generator. The turbine wheels are connected to the shaft. A turbine wheel consists of a round hub and rotating blades, or buckets as they're sometimes called. The shaft and the wheels are collectively called the rotor. The rotor is supported by bearings and is housed in a casing which is sometimes referred to as a cylinder. Mounted to the turbine casing are diaphragms. They are positioned in the casing between the wheels. The casing and diaphragms are stationary parts of the turbine. Diaphragms are similar to wheels in that they are round hubs and they have blades. The diaphragm blades are sometimes referred to as nozzles. The distinction between diaphragms and wheels is the way they function during turbine operation. Diaphragms are stationary and their blades are fixed in position. Their function is to direct the flow of steam leaving one set of rotating blades into the next set of rotating blades. Wheels, on the other hand, are moving parts. They are designed to turn as the steam flow passes through their rotating blades. The rotation of the wheels turns the shaft and the generator. Diaphragms are sealed where the shaft passes through them to minimize steam leaking through this opening and bypassing the diaphragms. Typically, the pairing of one diaphragm and one wheel is called a stage. A turbine may have up to 25 or more stages. Our example shows 8 stages, but only 7 interstage diaphragms. There's another diaphragm before the first row of rotating blades. This diaphragm is called either a nozzle block or a nozzle box. As with the interstage diaphragms, the nozzle block houses a series of stationary blades that are sometimes referred to as nozzles. The diaphragm nozzles direct the steam from the steam inlet to the rotating blades of the first wheel. The steam then proceeds through the remaining stages of the turbine until it is exhausted into the condenser. Now, before steam can enter the turbine through the steam inlet, it must pass through two types of valves: stop valves and control valves. Stop valves, which are also called throttle valves, remain fully open during turbine operation. The principal function of stop valves is to shut off the steam supply to the turbine during a shutdown or under emergency conditions. Control valves are used to regulate the amount of steam flowing to the turbine. For this reason, control valves are sometimes called governor valves. Under normal conditions, the control valves are partially open to regulate steam flow during operation. Steam flows from the stop valves to the control valves through pipes. Depending on the turbine design, steam may also flow through a steam chest. A steam chest allows the steam to spread out and slow down so that the flow will be less turbulent as it enters the control valves. In this part, we'll take a look at how turbine rotation occurs. As you may know, the function of a turbine is to convert the energy contained in steam into mechanical energy used to turn an electrical generator. This conversion is achieved by one of three methods: impulse, reaction, or most commonly, by a combination of both. While the end result is the same, the method of producing the result is quite different. Impulse blades work in a manner similar to the blades of a pinwheel. Air traveling in one direction strikes the pinwheel blades and pushes them out of the way, causing the wheel to turn. With turbine impulse blades, a similar thing happens. This simplified illustration shows the configuration of turbine impulse blading, with the rotating blades and the stationary blades or nozzles. As high pressure steam is forced through the stationary blades of a diaphragm, it speeds up. The steam striking the rotating blades causes the wheel to turn. Since the wheel is attached to the shaft also rotates. Reaction blades work differently. With reaction blading, the speed of the steam's movement causes the rotating blades to turn. This is easier to understand if we look at how a rocket engine is designed. This simplified illustration represents a nozzle that is part of a rocket engine. Hot gases from the combustion of fuel are exhausted through the nozzle as they leave the combustion chamber of the rocket. The nozzle causes the hot gases to accelerate to a high speed as they pass through the nozzle's narrow throat and then expand. The high speed creates a reaction force on the rocket engine that is in the direction opposite to the movement of the gases. This reaction force propels the rocket engine. In a turbine, the moving reaction blades act like the nozzle in a rocket engine. Steam leaves the blades at high speed and creates a reaction force on the blades, and that causes the wheels to turn the turbine shaft. Most modern turbines combine the use of impulse blades and reaction blades of the energy in steam. It is the designer's job to determine the proportions of each type of blade required in a turbine. Most large turbines are almost pure impulse in the first stage, almost pure reaction in the last stage, and a combination of the two in between. Now, you won't be designing turbines, but understanding what's going on inside will make you better equipped to operate them. So far, we've been talking about a simplified turbine. Most large turbines are divided into sections, and each section is connected to a common shaft. In this illustration, there are three separate turbine sections: a high pressure or HP section, an intermediate pressure or IP section, and a low pressure or LP section. At times, the different sections are referred to as separate turbines: the HP turbine, the IP turbine, and the LP turbine. But operationally, they all make up one turbine. In another turbine design, the sections are connected to different shafts. In this example, the HP and LP sections are on one shaft, and the IP section is on another shaft. This arrangement is called cross-compounding. While each section of a turbine works according to the same principles, they are not identical. By the time steam has traveled from the high-pressure section to the low-pressure section, its volume may have increased as much as 150 times. The size of the turbine is increased. Second, some of the steam is removed from the turbine by an extraction steam system. The extraction steam is sent to the feed water heaters, where it is used to heat feed water. The steam in the turbine gives up some of its heat as it passes from one stage to the next. For this reason, it's often necessary to return steam to the boiler for reheating before it passes through the entire turbine. This reheating most often occurs between the high pressure section and the intermediate pressure section. Reheated steam is returned to the turbine through reheat stop valves and intercept valves. These valves, along with the stop valves and the control valve, also provide protection for the turbine. As you know, turbine speed is regulated by the control valves. If turbine speed increases during normal operation, how do you think the control valves will respond? If turbine speed increases, the turbine control valves will compensate by closing. Under certain unusual conditions, the turbine may begin to overspeed. That is, the turbine may begin rotating at a rate higher than it was designed to handle. An immediate danger exists that the turbine speed will increase to a point at which centrifugal force will break it apart. This is where reheat stop valves and intercept valves help to protect the turbine. If the turbine begins to speed up, the control valves will compensate by closing. However, there is still a great deal of steam in the reheater section of the boiler. This steam will continue to flow through the turbine, causing it to speed up. To prevent overspeeding, the intercept valves close, cutting off steam from the reheater. If for some reason the speed continues to increase, the turbine trips. When the turbine trips, all four types of valves, the stop valves, the control valves, the reheat stop valves, and the intercept valves, quickly close, cutting off all steam to the unit. A trip protects the turbine from danger by immediately shutting off steam flow to it.
Okay, so that's about explanation on how turbine function. So we proceed to the next content. Okay, so that is the overall about the power station that using a turbine to rotate the generator to generate electricity. Yeah. So I hope that you can try to understand how the power station function, yeah, by looking at the main concept and how the mechanism of each power plant. Okay, now we look into the electric current that is produced. So what we can say that the electric current produced can be divided into two types. Yeah, that is what we call as a direct current, DC. So the DC stand for direct current, and the second one is a alternating current, AC. Yeah. So what is the difference and what is the function? What instrument use direct current and what instrument use alternating current? Okay, so we can see the direct current means we have one way of flow of electric current. Direct current means one way of direction. So direct current is an electric current that flows in one direction only. So one direction only. The devices that use this direct current is given here. For example, torchlight, calculator, toy car. Yeah, so direct current. Generators, example of generators or sources of electricity that produce direct current are shown here. Solar cells, accumulators, and batteries. Accumulators is a vehicle's battery to produce direct current. Okay, so alternating current. So alternating current is an electric current that flows in constantly reversing direction. So, example given here, the apparatus or using the alternating current. Okay, so what we can say is electricity from the generators in power station, they will produce alternating current. So electricity from power station, they will produce alternating current, in which the current that come from the power station, they will reverse back, coming back to the power station itself through the circle of the wire. But when this alternating current enter into our house, consumer house, so what will happen is, from the point of the alternating current outside the house into the house, so the current that will be used is a direct current. So from the outside current from the power station, and when enter into the house, so what will happen? The alternating current will be convert into the direct current. So to answer this question, do most of the electricity generators in power station produce DC or is AC? So most of the generators in power station produce alternating current. So alternating current, so in our house, most of the electrical appliances, so using the from the outside into the socket, from the outside into the socket, so using the alternating current. Okay, so that is the difference between direct current and alternating current. And now we look into this one. But this one exactly difficult to explain, because exactly we have a practical session on how to use what we call as a cathode ray oscilloscope. Cathode ray oscilloscope. So this is an electronic device that try to explain about the characteristic of two types of the electrical current. So if we want to know the characteristic of direct current and also the characteristic of alternating current, so we can use this CRO, cathode ray oscilloscope, in which this cathode ray oscilloscope can show you what is the shape of the graph produced, what is the direction of the current, and also the voltage produced from that current. So by using this instrument, so we know the characteristic of direct current and also alternating current. So difficult to understand this one. Exactly we have to do in the lab to show you about this one. So we skip this one. You just only maybe have to remember the button here, the knob using here. What is the function? What is the name for each knob given here? That's all. Okay, so the last thing in this subtopic is about the how innovation to generate electricity. So if anything happened to the power station in which the power station there is a experience disruption. So what will happen is, for example, in our country, Malaysia, we have TNB, Tenaga Nasional Berhad. So this TNB exactly manage all the power station. So if something happened to the power station, so they have manual generators to back up the supply of electricity during destruction of power station. Yeah? For example, this one, we call it as a genset. So this genset can be used to generate electricity, yeah, but in a small amount only. Yeah? Okay, so the last one, example of innovation to generate electricity. So you can read from this one, application, and then how the concept of generator is being used in any electrical appliances. For example, this one, wireless electrical transmission and distribution, energy changes, okay, to radio wave or microwave energy to be transmitted without wires to electrical device. So you can read on your own for this one. Yeah. So, and the last thing, as usual, I hope that you can write a note for this one until 6.1, and after that, please answer this question, formative practice 6.1, question number 1, 2, and 3. Yeah. Okay, so the next subtopic, next class, we'll proceed into transformers. Yeah, transformer. Okay, so before you left, yeah, wait a minute. I want to take attendance first. Okay, now we have 29. Yeah, 29. Okay. Okay, so that's all for today. So for next week, exactly we have a holiday, school holiday, but I will